these are the problems. One is the quality of the interface is not very good. The thermal stability is not very good. And also there's diffusion across the boundary between carbon and silicon. All right? So we went ahead and did, all right, why not we make some combined technology with SiO2. So we have what we call silicon and dual silicon, meaning that we have both the diamond and the SiO2. Now, with the presence of SiO2, diffusion is impeded because this is a barrier layer. And because of that, the transformation of sp3 to sp2 is retarded at the same time. So we are having a very nice look at the interface here. It's very neat, no problem. And also, thermally is a lot better. 1,000 degrees, you see the breakdown is the same as 700 and 800 degrees centigrade. So we don't have any problem anymore. With this structure, we're able to break up the temperature and not to kill the material. And this is a simulation of the temperature. If we use the old technology, the temperature at the channel goes up to 500 K, which is about 127 degrees centigrade. If we use our diamond structure, 360. So that means that the heat problem is alleviated. It's a lot less than before. So very good. But we haven't stopped that because we want to make things cheaper. So I'm going to talk about a new technology called hydrogen introduction by plasma hydrogenation. Previously, we implanted some energy. But we can actually do another way by low energy hydrogenation. Instead of implanting, it's diffusion. Diffusing hydrogen into the materials. And the thing to do that is to create a defect layer right here by implantation first. And then have the thing diffuse in. And after it diffuses in, you get bubbles. And the same idea, you bond with the wafer. And then you crack it. And then it works. So this is a much cheaper process. And the way it's done is we first form some defects. This is the SEM. Form some defects at this site by implantation. And then we draw the hydrogen ions in from the plasma, actually atoms, right here. Low energy, so a very cheap process. And then with the bubbles formation, we can do the cleavage. The obvious data shows that it's useful. Now we have hydrogen actually at the interface right here. We can detect hydrogen, so it's successful. And you can see the defects here. Very, very linear, so you can have a very sharp breakage at this point. And with that, we're able to transfer the layer from the top to the bottom. So this is very nice. So this is basically one step at a time. We improve the process. So much about electronics, you don't see these things. All right? When we talk about biology, you can actually see them. We do a lot of biology because material science not only has life, so it's interesting to look at biology. So here we have a lot of programs. Again, we look at surface biocompatibility, bioactivity, how these things grow with or compatible with cells, with bones, and so forth. We look at antibacterial coating, something that you want this thing to kill bacteria, conjugate. So we do that. We look at orthopedic impact, orthopedic 骨头. So we look at how the materials are being used. Cardiovascular, 心脏, 血管. All right. Dental, 牙, 口腔. So we also do that material. We do biodegradable materials, 可以降解. Naturally degradable materials that when the doctor put in your body, it will go away. You don't have to take them out. It's very interesting material. We do some science, surface micro and nano patterning for drug delivery, microfluidics, in the future. And last but not least, the newest area is nanobiology, 纳米生物. That's the next stage, okay? And also 传感器, biosensor. So we do all of that. So I'm going to show some examples of what we do. The first thing I'm going to show is to combine electronics and biology. We first of all look at the biocompatibility of silicon. Now silicon is a material used in computer, but not in the human body. Alright? But if you think about that, if you put a device, a sensor in your body, the sensor is made of silicon. So it's important to know how the sensor behaves in your body, whether the sensor is toxic or it causes any reaction to your body. Right? So you need to know that. So if you can make the silicon chip to be biocompatible, meaning that conducive to the growth of whatever cells, it's not harmful. You want to make the material non-harmful. Right? So here, we use our technology here, implanting hydrogen, and we are comparing two. This is just bare silicon. What we do is we take some blood your body, basically, and then we use simulated blood from the body, and then we put the piece of silicon in there and see if there's any reaction. If this is a normal piece of silicon, nothing happens. If this is a treated silicon, something grows on the surface, inside your blood. Okay, because it's a simulated molecule, which is the same as your blood plasma. So something is very interesting, meaning that after the treatment, you can get something to grow on single crystal silicon, which is a dead thing, right? What is this? So we look at the XRF, X-ray fluorescence spectrum, and we find this is made of calcium and phosphorus. Interesting. What is calcium and phosphorus? What part of your body has the most calcium and phosphorus? People take calcium pills. Guy, what part of your body has calcium? Anybody takes biology? No. Why do people take calcium? Ladies take calcium, right? Old people take calcium. Why? What does it do? Bone. Perfect. Calcium phosphate is your bone. Your bone is made of calcium phosphate. So that means we are growing bone on silicon. Isn't that interesting? Like God. We're building something from nothing. We just put the wafer in some blood, whatever, and bone will grow. Ah, magic. Let's see what happens here. This is a cross-section. The silicon wafer, we do have this layer. So we did some X-ray diffraction. We found a single crystal silicon, which is fine. We have an amorphous layer here. And then here we did some EDAX, X-ray analysis looking at the elemental composition. Region A has more calcium than phosphorus. Region B, less. And C is almost 2 to 3, which is the natural composition, Ca3PO42, right, chemistry. So 3 to 2. So this is about right. So that tells me something about the mechanism, how that goes. So that means calcium is attracted first, followed by phosphorus. All right? This is a very good picture, the first one ever that I think that we did, to show actually bone grows on silicon. This is the interface. This is a silicon wafer. You can see all the atoms. 2 nanometers this large. So this is much more small than that. Angstroms. Each one is an atom. Okay? So it's really high resolution. This is amorphous layer. This is your bone right here. Single crystal. Crystal structure bone. Apatite. It's a bone. Calcium phosphate. First time that somebody is growing bone on a computer. Huh. Interesting. How does it work? Well, if you have normal silicon, it doesn't work. What we have done is we've implanted hydrogen. So that means the surface is not hydrogenated. And then in water, this becomes O-, the hydrogen goes away. And then in the body fluid, you have calcium ions. They are attracted and become positively charged. And then the phosphate comes on, and you get calcium phosphate, and this continue and continue. That's why we have calcium rich at the interface, and then becoming more and more, or less rich, and become calcium phosphate. Beautiful. But this is only silicon. It's nice to play. Is there anything we can do to make it better? Okay. Let's look at some medical implant. This is a hip joint, right here. A lot of people break their pelvis, break the bone. Usually when you're young, you can recover. When you're really old lady, they won't like that. You have to put something in. This is a very typical device. It's a hip joint. They put a socket in your pelvis, and then they put the shaft inside your bone, and then connect this up. This surface rotates, so the legs